We're currently right in the middle of a global race, and I mean a massive, high-stakes push to electrify absolutely everything. We're talking everything from the cars we drive to the massive grids powering our cities. And at the very center of this modern industrial revolution is one single, totally critical element: lithium. Without it, the clean energy transition literally stops in its tracks. But as we're about to see in this explainer, getting this white gold out of the ground is sparking an entirely new environmental crisis. So let's dive into this. Okay, I want you to just pause for a second and think about this number. 15 times. That is the massive plot twist in our global energy story. Between the years 2020 and 2040, the worldwide demand for lithium is expected to absolutely explode by a factor of 15. We're talking about jumping from 74 kilotons to a staggering 1,160 kilotons every single year. The scale of extraction we need is something the world has rarely ever seen, and the pressure to mine this metal is building way faster than our current infrastructure can actually handle. And that immense pressure brings us to a really uncomfortable reality. The technology designed to reduce our carbon footprint may be causing harm to pristine natural areas. It's kind of the ultimate paradox, right? The very lithium-ion batteries that are meant to save our planet from climate change rely heavily on extraction methods that are, well, tearing up ecosystems and draining critical resources.
Section 1. Yeşil enerji paradoksu. The green energy paradox.
So to understand why this is such a massive dilemma, let's do a quick breakdown of how we actually get lithium today. Because right now, the industry is largely split between two dominant methods, and unfortunately, neither of them is what you'd call earth-friendly. It's basically a game of pick your poison. First, you have traditional hard rock mining. It's fast, sure, but it requires blasting rock and massive chemical processing, which emits an enormous 37 tons of CO2 for every single ton of lithium produced. Then, on the flip side, you have brine evaporation, which you see a lot in South America's Lithium Triangle. This method uses an unbelievable 2 million liters of water per ton of lithium. In some of the most arid, dry desert regions on Earth, that kind of massive water depletion is just absolutely devastating. And the toll of these methods is heavy. With evaporation, you pump lithium-rich water into these massive service ponds, and then you just wait for the sun to evaporate it. We're talking anywhere from 13 to 24 months. Think about how incredibly slow that timeline is. And during those 2 long years, it's depleting freshwater aquifers, it's disrupting local biodiversity, and it severely impacts the surrounding indigenous communities who absolutely rely on that water. These traditional methods are just way too slow and vastly too destructive to sustainably support an electric vehicle revolution. Which leads us to the most urgent question of the decade. Daha temiz bir yol var mı? Is there a cleaner way? Can we actually extract the resources we need without destroying the very environment we're trying to save? Well, scientists and engineers haven't just been sitting around. They might have actually found the ultimate solution to this problem.
Section 2. Doğrudan lityum çıkarımı. Enter Direct Lithium Extraction.
This is a massive technological breakthrough that could completely flip the script on the green energy paradox. So what exactly is direct lithium extraction, or DLE? Well, it's not just one thing. It's actually a suite of modern technologies, using incredibly smart concepts like sorption, ion exchange, and high-tech membranes. Think of it less like a giant slow-motion evaporation puddle and a lot more like a highly advanced rapid water filtration system. It selectively pulls the lithium out of the brine incredibly fast, while leaving the rest of the water intact. Instead of sprawling, man-made evaporation ponds taking up thousands and thousands of acres of sensitive desert, a modern DLE chemical processing plant is totally different. It's an integrated, highly controlled, closed-loop facility. It's essentially a sleek, modern factory, which drastically shrinks the geographical footprint of the whole mining operation. The truly crucial point here is how DLE completely outmaneuvers older methods. First off, it crushes the timeline, taking production from 16 agonizing months down to a fraction of the time, literally just days or hours. Second, it aggressively lowers the water footprint by recycling the brine and re-injecting it right back underground. And third, it drastically limits land use and protects those precious freshwater aquifers. Plus, if you power these high-tech plants with renewable energy, you can heavily reduce the overall greenhouse gas emissions of the entire process. It's a real game changer.
Section 3. Yeni teknolojinin ekonomisi. Economics of the new tech.
But listen, environmental miracles still have to make sense on a balance sheet, right? Because if DLE bankrupts the companies trying to use it, it's never going to scale up to meet global demand. So let's look at the setup costs, the capital expenditures, or CAPEX. Building a DLE plant is expensive, between $45,000 and $80,000 per ton of capacity. That is noticeably higher than just digging solar evaporation ponds. But look at the OPEX, the day-to-day operating costs. DLE costs about $4,500 to $7,500 to run, which is highly competitive with traditional evaporation and vastly cheaper than the $6,000 to $18,000 it costs to run hard rock mining operations. The long-term math actually works. We do need a quick dose of reality here, though. As the quote goes, some tout DLE as the holy grail for lithium production, but experts caution success is not yet proven commercially. While DLE is incredibly exciting and allows us to tap into completely new sources like geothermal and oil-field brines right in the US, it's largely untested at the massive planetary scale we're going to need. It is a brilliant, promising prototype, but it needs to graduate to a global standard and fast.
Section 4, Lithium'un geleceği, the future of lithium.
Let's propel this narrative forward and look at the looming supply crunch and the rapidly shifting regulatory landscape shaping tomorrow's energy grid. We are on a bit of a wild roller coaster. As of 2024, the market is actually slightly oversupplied because electric vehicle sales temporarily slowed down, while a bunch of new mining projects came online. But don't let that fool you. Analysts project a severe supply deficit crashing toward us by 2028, and if we look further out to 2050, the battery sector alone could exhaust up to 248% of our current known economic reserves if we don't drastically change how we source and reuse this metal.
Which makes our current situation incredibly hard to stomach. Right now, a shockingly low 5% of lithium-ion batteries are being recycled. That means 95% are ending up unrecycled or just sitting in landfills, leaking harmful forever chemicals known as PFAS into the environment. Experts estimate that a robust recycling economy could eventually meet up to 50% of our lithium demand. But right now, we're practically throwing away the very resource we're tearing up the earth to find.
The good news? Governments are finally stepping in. The European Union has proposed stringent new regulations requiring strict environmental and social standards for all lithium imports, which is forcing the industry to boost recycling. Meanwhile, the U.S. Department of Energy is pumping billions of dollars into funding DLE projects and domestic mineral production. Cleaner extraction and a circular economy aren't just moral choices anymore, they're becoming the law.
And that brings us to the ultimate overarching question. İklim hedeflerimizle doğanın korunması arasındaki bu hassas dengeyi nasıl kuracağız? How will we balance our climate goals with the protection of nature? We absolutely need lithium to power a sustainable, fossil-free future. DLE technology offers an incredibly exciting, high-tech bridge to get us there with far less damage. But making that a reality requires a massive, complex balancing act between innovation, economics, and ecology. Thank you so much for joining me on this explainer today. I hope you leave not just understanding the problem, but feeling empowered by the incredible science working to solve it.